Okay, so chapter 30 is about the nature of the atom. And when you talk about the nature of something, you're basically talking about how it behaves. Like National Geographic, they talk about the nature of the hyena. How does it act? Okay, so that's what this is all about. How atoms act. And so it's based off of all of these ideas that we've talked about, starting from Rayleigh Jeans, Planck, Max Planck. Who else came into the picture? Einstein with the photoelectric effect, Compton. So let's talk about that. The Rutherford scattering experiment, 30.1, just talks about how I think these Austrian Ernest Rutherford ran an experiment with alpha particles, and he basically discredited the Jellium model. What he found was that with the Jellium model was the idea that material was made up of this sort of background of positive charge, just evenly or uniformly spread out through space, and there were negative charges, electrons or negative particles scattered within this uniform positive charge, and that's why they call it the Jellium model or the plum pudding model. Where the pudding part or the jelly part was the positive charge, and the seeds in the jelly were the negative charges. But what he found was that when he had this sort of contraption where he was firing alpha particles, or positively charged particles, are basically hydrogen atoms with the electron stripped off at this target. And what he was seeing was that some of the alpha particles were recoiling back. Some of them were scattering at different angles, but some of them were going straight through. Now, if this whole thing was just one uniform positive field, you wouldn't have this kind of scattering. This scattering kind of indicates that, there are solid positive charges in there. Because these are positive charges. The alpha particles are positive charges, and the only thing that's going to repel them are other positive charges, according to the theory that they had at the time. And the theory we still have now, positive charges repel. So, if this was one uniform positive charge, you'd have the alpha particles recoiling the same way every time, but some of them were passing through, some of them were scattering, as if you were trying to throw a ball through a fence, or some marbles through a fence. Some of them are going to hit the little metal, some of them are going to go right through the holes. So what this gave him the idea was that charge is not uniformly distributed throughout matter. It's actually concentrated at little points, points part. And so this is the beginning of our concept of the atom. Charge, positive charge being positive charges being particles and negative charges being particles. They're both particles, not one being a particle and the other one being a uniform background. Okay, so Rutherford said, well, if the charged particles, if the positive charge is being concentrated or centralized in a particle, and the negative charges are concentrated and centralized as particles, then what's stopping them from just joining together and canceling out? If they're just floating around in space. So he came up with this planetary model he said the electrons must be orbiting the positive charges like the moon is orbiting the Earth, and there must be some kind of the electrons must be orbiting the protons at a certain speed such that they don't fall into the Earth. something like, So that's why we have this idea of, you probably seen the, if you Google physics and in Google Images, you'll come up with that symbol, of an atom there with electrons orbiting a nucleus, right? So this is how the idea of the atom started building up. Okay, but there was still, something not right about this model, because what they knew at the time was that when electrons accelerate, they radiate energy. They give off energy. So if they're giving off energy, that means that their velocity has to be decreasing, because they're losing kinetic energy. So if they're losing kinetic energy, they shouldn't be orbiting in a circle. They should be spiraling into the nucleus. But they didn't have anything to explain that at the time, and so that's the way science is. When you don't have an explanation, you just leave the hole there. You don't try to plug it in with magic or anything. You just say, okay, well, maybe someone somewhere else will figure out what's going on. So one of the next contributions was this idea of line spectra. What they noticed was that when you that if you pass light, if you shine light on, say, a gaseous material, all these different rays. Okay. Thank you. You're welcome. Some of the light passes through, and some of it doesn't. And you also have re-emission of some of the light. Okay. And for different elements, for example, neon, mercury, krypton, they only absorbed and emitted light at certain frequencies or certain wavelengths. And if you mapped out those wavelengths, say these bars represent the electromagnetic spectrum. Okay, say the visible light spectrum. This is just that segment. You would see that neon would have these fringes, or these collection of bands concentrated at different parts within the spectrum, and mercury would have its own, unique set of bands. These are called line spectra. So there are a few guys that tried to explain or tried to come up with mathematical formulas to reproduce these line spectra, and that's what these series are all about. The Lyman series, the Balmer series, the Postgen series. They're all different attempts to explain the emission spectrum of the hydrogen atom. The Lyman series is for short wavelengths. They couldn't get one formula that recovered the entire spectrum for hydrogen. So they just did it piecewise. They said, okay, it's for this formula works for, and they're all empirical formulas. So this formula works for the short wavelengths, and then for the Lyman series works for short wavelengths. The Balmer series works for the mid-range wavelengths, and then the Postgen series works for the parts of for the short wavelengths or high energy emissions. Okay. Then Bohr came up with an idea that for the hydrogen atom. He came up with a model of the hydrogen atom with this planetary model where the electron is orbiting the nucleus, like the moon orbits the Earth, or the Earth more orbits the sun. And in order for his theory to work and explain these emissions, these discrete emission phenomena that you see. Okay, he said that, okay, well, the electron is orbiting the nucleus of these atoms, but they must orbit them in stationary states. Okay, they can't be in any kind of continuum state. So if I have an orbit of r here, and say r equals, I'm just throwing out a number now, 10 angstroms, say, for example. I'm just throwing out a number. I can't have another orbit here that's slightly larger, or 10.1 angstroms. Now, an angstrom is a unit of length. It's 10 times 10 to the negative. It's 1 times 10 to the negative 10 meters. Okay, I can't have 10.1 angstroms. I can only go in discrete orbits around the nucleus, and he called those stationary states. And later on, Wolfgang de Broglie, with his description of the de Broglie wavelength and his implementation of the wave-like behavior of particles, with that added to the Bohr model, it helped plug in that hole that I was talking about in the theory as to why electrons don't radiate away all of their energy and spiral into the nucleus, because at these small dimensions, electrons behave like waves, not like particles. So you can only have standing waves in a circle, in a circular orbit around the nucleus. And because of that, you have all kinds of implications. One of them is discrete energy. Okay? Because you can only have standing waves around the nucleus. Okay? Particles only, or electrons, or atoms can only take on discrete energies that depend on these standing waves propagating. Electrons acting as standing waves, are being described as standing waves about the nucleus. Okay, so what are some of the implications that I'm talking about? One is discrete energy. Okay, which is described by equation 30.4, which says that the initial energy of a hydrogen atom that's transitioning to another energy state will only transition that energy state in certain quanta, or certain leaps. It can't go in a continuum. Okay, so that means that it has to release energy in a certain in discrete packets, and those discrete packets used to be called quanta. We now call them photons. So what that means is that an electron or a hydrogen atom will not change its state unless it absorbs a certain amount of energy, a certain discrete amount of energy. Okay? If it gains some energy, it will go up to another energy state, but it will only be an energy state as described by equation 30.13. If it loses energy, it will only go from one state to another as described by equation 30.13 again, and it will release a photon, and that photon will have an energy that's the difference between those two energy states that the hydrogen atom is transitioning between. Okay? All right, so that's what's described in chapter 30. Discretization of energy, or quantization of energy, and quantization of angular momentum, quantization of radius of orbit. Okay, that's 30.10. And this quantization of angular momentum, we worked out in class. It also comes from these stationary states of atoms. Okay, where you know that L, your angular momentum, is going to be I times omega. Okay, where I is your rotational inertia for a particle orbiting a central axis, orbiting an axis, okay, at a radius r, having a mass m, so it's going to be r squared times omega, okay, and we know that velocity equals omega. The velocity of that particle will be whatever its angular velocity is times r. Okay, so this is mr omega. I'm sorry, mrv. It's one of those r's. Okay, and this discretization comes in where they say that R is only going to be certain wavelengths. Okay. Okay. All right. So what this is saying is that this is what Wolf de Broglie contributed to explain the stationary states that Bohr could not explain. He said that at this level, particles are not behaving like particles anymore, scattering like billiard balls on a pool table. They're behaving more like waves of light, interfering, diffracting, and all this other thing. So treat them like a wave. Don't treat them like a particle. And just say that, okay, instead of thinking of an electron orbiting the nucleus, like the moon orbiting the Earth, think of a standing wave in a chamber, at resonance, okay, where you have whole wavelengths filling up the length of the chamber. Instead of thinking about the length of the chamber linearly, think of that sort of in polar coordinates and wrap this wave around the hydrogen atom. Okay, so if you wrap it around the hydrogen atom, this L, this distance, this length of the chamber, the dimension of the chamber is the circumference of the orbit. Okay, and so so that's 2 pi r, where r is the radius of the orbit, and then you say that orbit, or the waves that you wrapped around the hydrogen atom, you can only fit integral wavelengths around the atom. Only 1 wavelength, or 2 wavelengths, 3 wavelengths, 4 wavelengths, 5, whole wavelengths, not partial wavelengths, not fractions of wavelengths. So that's what this part of the equation means, n times lambda. Okay, so if you do this, so if you discretize, or you say that these particles are acting like waves, and they only orbit the atom in whole wavelengths, okay, then that means that that's going to have certain implications on your angular velocity. Okay, what are those implications? Well, that's going to mean that r can only take on these values in 2 pi over n lambda over 2 pi. Okay, de Broglie also stated that when particles act like waves, their momentum is related to their wavelength according to this equation, where h is Planck's constant, p is the momentum, and lambda is the de Broglie wavelength. Okay, so when you substitute that into here for lambda, you get over 2 pi, you get h over momentum. Okay, and then when you substitute r into this equation, then you get L equals mv mv times r, which is this, nh over 2 pi times the momentum. But if you recognize this is momentum and this is also momentum, so they cancel out, so you get nh over 2 pi. So that's how you get that equation in your book, discretization or quantization of angular momentum, 30.8. Okay, so let's work out a problem from that uses this idea of quantization of energy. Okay. Okay. So let's look at number 10. We have the electron in a hydrogen atom is in its first excited state. When the electron acquires 2.86 EVs of energy, what is the quantum number of the state in which the electron moves? Okay, what state when it absorbs that energy? So this is why we're saying that the hydrogen atom can only take on certain energies, as described by that equation. En equals 13.6 times z squared over n squared. Okay, so just memorize that, or keep that in mind as we work out this problem. So we have a hydrogen atom. Okay, and we have an electron orbiting the hydrogen atom. Even though we just discussed that it's more like a wave, a standing wave wrapped around the hydrogen atom. Okay, but this is easier to draw. We blow this up. All right, so the electron is in a hydrogen atom is in its first excited state. And in its first excited state, that means, as we were saying before, n equals 1. Okay, so E1 is negative 13.6 times z squared over n squared. All right. Okay, so that's the no, that's not the first excited state. This is the ground state. The first excited state is E equals 2. Okay, and this is a hydrogen atom, so Z equals 1 because you only have one proton in the nucleus. Okay, so there we go. That's the first excited state. First excited state, ground state, second excited state. All right, so the electron acquires an additional 2.86 EV of energy. Okay, so the final state is the initial state plus 2.86 eV. What is the end state, the quantum number end state to which the electron moves? Okay? So what do we do here? Why don't we do this, okay? Let's describe EF in terms of its quantum number n, okay? And let's go ahead and calculate what E2 is. So E2 is negative 2, this over 4, okay? Plus 2.8 eV, okay? En is 13.6 times, this is the hydrogen atom, so this is just 1 over n squared. And that'll, if we calculate this and solve for n, we'll have the state, okay? So let's work this out. So let's see. Negative 13.6 divided by 4 plus 2.86 negative 0.54. Is that what you got? Okay. Now let's do a little algebraic simplification here. That's going to give me negative 13 over negative 5.4 equals n. Okay, so n equals the square root of 13.6 over 15. Over 0.54, square root of that. Okay, so this is 13.6 divided by 0.54. Get the square root of that. N equals 5.01 something. So it's in the fifth state. So that means the first excited state, second, third, fourth excited state. Okay? Where n equals 1 is the ground state. So you see what I did? All I did is say, okay, this is my initial, this is my E sub I, my initial energy. And I describe my initial energy as E n equals, I describe all my energies this way, actually, over z squared over n squared. Okay? And then they told me that it gained this much energy. So I just add these two energies together to find my final energy. And then I just describe my final energy in this form to solve for n, and then solve it for n. Okay? All your energies of the hydrogen atom are going to have this form, right? So energy, any number I give you, if I say the energy is 7.67 eV, you just say, okay, you equate that energy to this equation, and you solve for n or solve for z or whatever I'm asking you to find. If I ask you to find what's the number of protons in the atom to identify the atom, then I give you this prime number n, then you solve for z. If I'm asking you what the state of the energy of the quantum number state n, which is called the prime quantum number, you can solve this for n. So this is energy equals the number of protons squared divided by n. And this negative 13.6 comes from a derivation that's in your book. Yes, Ms. Brown.
Okay. So since you're just adding like a one question from this chapter to the test, would it be safe to say that the equation is going to be focused on?
Pretty much, you know, that it might be a three-part question that might involve.
But it'll use that formula mostly.
Yeah, if you want to describe the energy of a hydrogen atom, use that equation. If you want to describe the energy of a multi electron atom, use this equation. That with one electron, use that equation. If it's got more than one electron, you can't use this anymore. But you're not gonna have to deal
You
with
can
that.
still use that one though, right?
Yep.
Okay.
Yep. That's the
So
energy
then-
of a hydrogen atom.
For example, if you were to do a problem like number 11,
Okay, what does 11 say? Find the energy in joules of a photon that is emitted when an electron in a hydrogen atom undergoes a transition from 7 to produce a line in the Postgen series.
and those are like the higher energy levels, right? I mean lower.
Yeah, the Postgen is the longer wavelength, so yeah, lower energy. Yep.
So how would you do something like that? Because your Postgen series, you can use, there's different ends that are possible.
Right,
So
right.
would you just like, if you were to do something like that, would you choose one more specific, like from n set equals 7 to n
To
equals
something.
5?
Yeah, yeah. Seriously. So let's look at this one. Find the energy in joules of a photon that is emitted when the electron in a hydrogen atom undergoes a transition from 7 to produce a line in the Postgen series. Oh, okay. So in the Postgen series,
It's like 4 or 5.
all of them go from n to, in the Postgen is telling you that other n that you want. In the Postgen series, that other n is 3.
Oh,
So
okay.
so it's just given. When they say Postgen, it's
Okay.
given 3. When it's Balmer, it's given as 2. So you got it. So you understand what you need. Okay.
But how would you, so that, oh, never mind. So we would still use that equation to find the energy difference, but you would just use n is 3.
Yeah. What happened was that this is what they came up before the Postgen series, the Balmer series, and the Lyman series. They were all empirical equations. They didn't understand why they would work. There was no theory behind them. They were just trying to fit some functions to what they saw. And so they didn't really know what this R was. They just put a fudge factor here to make it fit the data. But then they came up with this, and you see that this equation is very similar to the Postgen series, and they had some theory behind it this time. They knew that there's z squared was here, and they knew that what R was, and they had a n final and n initial. So this is just like a kind of primitive, and then this is more advanced. So you can use this
Okay.
and get everything that you need. Yep. And but for that problem 11, you just
Plug in 3 as your other.
yeah, as your other n, and then your 7 is this n, and then you find that wavelength, and from that wavelength you can you know that your energy, they were asking for energy in joules. So you know that energy equals Planck's constant times the frequency of the photon. But since you don't have the frequency of the photon, you can use the speed of light and solve for the frequency and use,
Plug that.
yeah,
Okay.
that's the energy. Yep. And that'll give you your energy. Okay. Let me see. There's another problem that I wanted to work. I think 35. Let me see. I think this particles and waves. Okay. Yeah. So this is another problem that I wanted to have a look at.